Okay, I can use this. Ah, okay.
So let's see here in Huisong lead, she will talk us about semantic-directed clumping of disjunctive abstract states.
Thanks. So I work together with François, Bérenger, Chang, and Xavier. Oh. So the purpose of this talk is to discuss how to improve the handling of disjunctions in shape analysis. Shape analysis focuses on analyzing programs dealing with unbounded dynamic data structures like lists and binary search tree. It aims to prove memory safety and functional properties like absence of no-pointer dereference and structure preservation. Most shape analysis work are based on forward abstract interpretation. It tries to compute loop invariants and post-conditions automatically from preconditions. Many of such analyses build abstract domains using separating conjunction and inductive predicates like list predicates and tree predicates. An example is concrete memory with a concrete list that from a pointer h can be abstracted by the abstract state, which is a separating conjunction formula. And in this talk, we always present these separating conjunction formulas as a graph to make the talk more intuitive and graphical. So in this abstract state, the two red edges starting from the node h abstract the first list element, respectively, for the next field and the data field. And the black edge labeled with list predicates abstract the list tail. However, disjunctions are often necessary in shape analysis. As an example, if we start from the abstract states, which abstract all the concrete list pointed by a pointer h, and analyze a simple program which tries to search the minimum and the maximum element from the list. Then, at the end of the while loop, we need to infer a disjunction of these two abstract states. And the first one abstract all the concrete memories where the minimum element appear in the list before the maximum element. And the second abstract state abstract all the concrete list where the maximum element appear in the list before the minimum element. However, keeping all disjuncts are expensive, as we all know, because without merging, disjunct number grows exponentially in disjunctive forward abstract interpretation. As an example, to read the next field element of the list head from this abstract states, we need to consider three cases where h is equal to min, and h is equal to min, but h is not equal to min, and h is equal to min but not equal to max, and h is equal to min and equal to max. Actually, each of these cases will correspond to an abstract state that we need to consider. Furthermore, a simple if-else statement will double the disjunct number that we have to deal with. And then if we put this branch statement into a while loop, each iteration will double the disjunct number. Therefore, for scalability, disjunct number should be kept small because fewer disjuncts means lower analysis cost, but merging disjuncts may lose precision. Therefore, deciding how to merge disjuncts without losing too much precision is critical. Existing techniques to deal with disjunctions include disjunctive completion, which builds the disjunctive abstract domain by using the power set of the analysis domain. Therefore, it only works for finite abstract domain, which is less expressive, and it's also often very expensive because it allows all disjunctive abstractions. Canonicalization allows the analysis domain to be infinite, which is more expressive. It first used a sound normalization, which maps the infinite analysis domain to a finite subset of it, and then use the power sets of this finite subsets at a widening point to compute loop invariance. Therefore, the expressiveness is restricted by the finite subsets. Also, it can be very expensive when the finite subset is very big. To use partitioning approach, we first need to define a finite partition criterion, and then use the lattice, which maps the partition criterion to the analysis domain. Common partition criteria include control flow and context extra, but such criteria tend to not work effectively for shape analysis. Therefore, we need a semantic technique to deal with disjunctions in shape analysis. In this talk, we propose silhouette abstraction. Silhouette abstraction is an abstraction of abstract states that characterize when abstract states join works well and when disjunctions are necessary. Based on the silhouette abstraction, we propose silhouette guided clumping of disjunctive abstract states, specifically the clumping strategy, which avoids joining abstract states when there is no precise list bound, and also the guided joining, which use silhouette join to guide the abstract states join to compute a more precise upper bound. Finally, we evaluate our technique on real-world syllables. Before introducing silhouette, let's first see when join will lose precision. To join these two abstract states M0 and M1, we need to compute an upper bound of them. Here is below, we show two upper bounds, which are both precise. The first one will lose pointer max, and the second one will lose pointer min. Actually, these two abstract states do not have several incomparable and imprecise upper bounds, but there is no precise upper bound. Therefore, joining them will definitely lose precision. We observe that the pointers order in data structure has a big impact on the join precision. This when pointers are in different orders, join tends to be very imprecise. As shown in our example, in M0 and M1, pointers min and max has different order. Therefore, to quickly identify imprecise joins, we need silhouette to abstract the pointers orders. Formally, we define silhouette as a graph where nodes are pointers values and the edges are labeled with access path string over fields. It means that starting from the source node, by following the access path string, we can reach the destination node. A very important property of silhouette is an abstraction of abstract states. As an example, the concrete memory can be abstracted by the abstract states, where the two edges starting from the node H abstract the first list element, and the two edges starting from the node min abstract the second list element pointed by pointer min. And the green edge labeled with list predicates abstract all the list elements starting from the next element of the element pointed by min and to the previous element of the element pointed by max. And also the red list edge abstract all the list elements starting from the element pointed by pointer max. And furthermore, these abstract states can be abstracted by the silhouette on the side, where all the red edges in the abstract states are abstracted away from the silhouette, and also all the green edges are abstracted by the access passes in the silhouette. Furthermore, the list predicates on the green edge is abstracted by the access pass star. Here, actually, the list predicates is a precise abstraction for list, while n star only abstracts the next pass, the access pass following the next field of the list. Another very important property of silhouette is it offers a quick abstract entailment check. Indeed, here we have silhouette entailment check, which is an algorithm that we use to decide the inclusion of silhouette. And also we have abstract state atonement check, which is an algorithm that decides inclusion of abstract states. We found that the silhouette atonement check offers a weak characterization for abstract state atonement check. Formally, it means that if the atonement check holds on abstract states, it also holds on the silhouette of abstract states. On the other hand, it means if the atonement check does not hold on the silhouette of abstract states, then we can conclude it does not hold on the abstract states. Based on this property, and also that the silhouette atonement check is much cheaper than abstract state atonement check, we can use silhouette atonement check to decide quickly when abstract state atonement check does not hold. As for silhouette join, it also offers a weak but precise characterization for abstract state join. And this set up the basis for our clumping. And also silhouette join is much cheaper than abstract state join because we simply need to replace excess passes with their over approximating regular expression. For example, here abstract states M0 and M1 cannot be joined precisely because min and max are in different orders in M0 and M1, and their silhouette can also not be joined precisely. Another example, here we have abstract states M2 and M3. In M2, pointer H and min point to the same node, and in M3, pointers min and max point to the same node. We found that abstract states M2 and M3 can be joined precisely, and their silhouette can also be joined precisely. Therefore, based on the good properties offered by silhouette join, we propose silhouette guided clumping. That is, given a disjunctive abstract state, we first need to compute a silhouette for each abstract state, and then we grouping silhouettes which can be joined precisely. Here, this grouping is based on an equivalence relation which captures precise silhouette join. Based on the grouping of silhouettes, we can get correspondingly we can get a grouping of abstract states, and then to reduce the disjunct number, we need to join abstract states which are in the same group. As an example, to perform clumping on these four abstract states M0, M1, M2, and M3, we first need to compute the silhouette for each of them, which is shown below. Then we can group the first three silhouettes together because they can be joined precisely, and leave the other silhouette alone. Correspondingly, we can get a grouping for abstract states. Then we can join the first three abstract states together and leave the other one alone. By this joining, we will reduce the disjunct number from 4 to 2. Now we have talked about the silhouette and the silhouette-guided clumping strategy, which will avoid joining abstract states with no precise list upper bound. Next, we are going to talk about silhouette-guided joining, which will use silhouette join to guide abstract state join to compute a more precise upper bound. To join two abstract states, we need to compute an over approximation of them. Existing joining work over rely on syntactic-based rewriting rules, where different rewriting order will produce different results with different precision. As an example, to join these two abstract states, we can first introduce a list segment from H to min, and by following a rewriting rule, and then introduce a segment from min to max, following the same rewriting rule. Finally, we can match the list edge starting from the max node, and get a list edge is output. Therefore, we can get a precise writing result that we want. However, we can also first introduce a list segment from H to max and then match the list edge from max. In this case, we will get an imprecise writing result because we lose pointer mean. And also, following different writing order, we can also get the other two imprecise writing results. This one will lose pointer max, and this one will lose pointer min and max. So the problem is, how can we always make the rewriting algorithm follow the correct order to compute a precise rewriting result that we want? We propose silhouette guided abstract state join, where we use silhouette join to guide the abstract state join to compute a more precise result by selecting which rewriting route apply and also helping to synthesis inductive predicates. The reason is that silhouette join is often an abstraction of a precise abstract state join result. Following the same example, here to join these two abstract states, we can first join their silhouette together. Then we use the silhouette join result to guide the abstract state join to introduce a list segment from H to min and from min to max. Finally, we can get a precise rewriting result that we want. Okay. Now we want to evaluate our technique. We set up 3 evaluation goals. We want to evaluate that clumping with guided joining effectively avoid precision loss, and clumping computation has reasonable overhead. Also, clumping limits disjunctive explosion. We set up 26 benchmarks, which varies in both data structure and the implementations. Specifically, we have some basic operations of binary search tree and a list from DSL library, and some operation on red-black tree and split tree from BSD library, and some operation on AVL tree from another library. To evaluate that clumping improves precision, we set up several strategies, including clumping with guided joining, clumping without guided joining, canonicalization with guided joining, and canonicalization without guided joining, and none. Here, none means we always 1-to-1 disjunct. We collect the number of verified benchmarks using each strategy. We found that clumping with guided joining successfully verify all the benchmarks, but canonicalization with guided joining only verify 21 benchmarks, and none only verify less than 10 benchmarks. Therefore, we say we can conclude clumping with guided joining improves precision. Furthermore, by comparing the number of verified benchmarks using clumping with guided joining and clumping without guided joining, we found that guided joining has an impact on the precision too. To evaluate that clumping has low overhead, we collect the percentage of the analysis time spent on clumping, abstract state join, and the others. We found that silhouette computation and silhouette join, which is shown in the black color, only take a few % of the analysis time in the worst case. Abstract state join is very expensive, which is shown in the green color, is a very expensive analysis operation. In the worst case, it takes about 50% of the analysis time. Therefore, we conclude clumping has low overhead, and also that compared to abstract join, silhouette computation and silhouette join is a very cheap operation. To evaluate that clumping limits disjunctive explosion, we collect the number of cyclic control flow passes for each benchmark, and the maximum disjunct number of loop invariants computed by our analysis, and also the maximum disjunct number at any program point, and also the disjunct number at the program exist point. We found that the loop invariants computed by our analysis always has a very low disjunct number. And also the maximum disjunct number is also very low compared to the control flow passes, which can be the disjunct number computed by analysis based on partitioning on control flow passes. Finally, we found that at the program exit point, the disjunct number is often only 1. Therefore, we conclude clumping limits disjunctive explosion. And also, even when we analyze a series of basic operations like insert, search, and so on, we found that the disjunction size will not explode exponentially. To conclude, disjunctions are often expensive in abstract interpretation, and merging disjuncts may lose precision. Therefore, we propose silhouette, which is an abstraction of address states, and we propose silhouette guided disjunct clumping, which rely on silhouette to detect imprecise join, and we propose silhouette guided joining, which use silhouette join to guide abstract states join to be more precise. Finally, we evaluate our technique on real libraries, and it shows that our technique effectively prevents disjunctive explosion and also avoid precision loss. Thank you. 14? Okay. I think in all the test cases that we have, it's always, but we didn't prove it's.
So you think you could come up with examples, maybe strange examples where?
I think it's possible because it's an adjustment. So.
Analysis-based partitioning can be done dynamically, like you call your join function and you select what you want to do according to the rules that you gave, or they can be implemented sometimes by pre-processing and exploding your program into another program, or by adding observed variables. Have you thought of the second way of implementing it rather than doing it dynamically?
No, sorry, I didn't think about it.
So you said that silhouette is production of parser state.
Yes.
The way it works is independent from the way you parse states, or it's built alongside the production?
It's built from abstract states. So when we want to perform a clumping, we first compute the silhouette from the abstract states, and then we perform clumping on the silhouette, which gets the clumping of abstract states.
I mean, the production state for which you build the silhouette are particular instructions, or you can assess state in different ways, and you can still perform silhouette.
You mean the original abstract states?
Yeah.
We only did the experiment from abstract states based on separating conjunction, but I think it could also maybe work for abstract states based on some other technique like TV array or something else.